index, not products.
Okay, let's get started. So before I leave the floor to David, let me just first collectively, at least from those of us in the region and the members of the committee, want to thank Ricardo, because while we did the selection, we couldn't have done anything if it weren't for the legwork by Ricardo in the back, of course, and of course the support from the ICTP. So I'll just tell you a little bit. So this prize every year, we select a winner and then some honorable mentions. The winner is David Camarena. But before I give the floor to him, let me just say there are two honorable mentions who are Luis Longo from the University of ABC. He's a PhD supervisor with Cecilia Chirenti, some of you know her, and Guillermo Rando de Oliveira also from the University, well, not from the University of Victoria. His PhD supervisor is Felipe Tovar Falciano from CBPF in Rio. So the prize comes with an invitation to a conference or a workshop to give a talk, a certificate. So this is to David, and some envelope that he'll get next tomorrow. But let's thank David. We're here about cosmology.
Okay, well, thank you very much for the introduction and of course for the prize. It's actually a great honor for me to be awarded with this prize in classical gravitation and applications. I'm currently a postdoc at the University of New Mexico, but I got my PhD here in Brazil in the Federal University of Espírito Santo in an international program for PhD in cosmology, astrophysics, and gravitation called Cosmo, which I believe Professor Ricardo also been part of, right? My PhD advisor was Professor Valerio Mara. So unfortunately, the topic of my thesis is not related to gravitational waves, so I hope you find these discussions or these results that I'm going to present today quite interesting, or at least a little bit interesting, right? So, working. It's yeah, so the first one. Okay, so when we talk about the standard paradigm of cosmology, we actually are talking about a set of fundamental assumptions that we use to build out a theoretical or mathematical framework that we later will use to interpret our cosmological or physical data. These conjunctions of fundamental assumptions somehow rise a cosmological recipe. And the main ingredient of this cosmological recipe is a theory of gravity. Oh, it's the other button, sorry. A theory of gravity, which are the particles and fields that compose the universe, and some assumption about the geometry or the geometrical symmetries that appears in our universe. And these three particular ingredients in the standard picture are the general relativity, the standard model of particles, the assumption that exists a cold dark matter component, and the assumption that the dark energy component, which is the component that drives the accelerated expansion of the universe, is a cosmological constant. But there is also another basic assumption, a very fundamental assumption that we make in the standard paradigm of cosmology. It is the assumption that our universe is isotropic and actually follows Copernican. And the Copernican principle just states that we don't occupy spatial place in the universe, and we are just merely biblical observers. These two assumptions are quite important because they establish that our universe can be well modeled through the Feynman methods of the classic perturbation. So what I would like to discuss with you today, it is that we can use cosmological data to test the assumption of the Copernican principle in the same way that we use cosmological data to test another assumptions. And this is just a particular example coming from one of the papers of the Planck collaboration, in which they test the assumption of general relativity using a modified gravity parameterization, and the assumption of the cosmological constant using a dynamical derivative parameterization. And these are kind of, let's say, examples of how we can use cosmological data to test the fundamental assumptions that we use to build out the theoretical framework of the standard cosmology. So saying that, I will try to argue how we can use inhomogeneous cosmology to again test, observationally test the Copernican principle. Later, I will present my result, which will be divided in 3 parts. The first one, which basically discuss what are the constraints that we obtain the Copernican principle using the current cosmological data. The second one will be about how we can improve our constraints on our knowledge of the Copernican principle if we use the next or consider the next generation survey data. And the last one will be what is the relation between the Copernican principle and the so-called Hubble tension, which is one of the most important problems that people is dealing with in cosmology nowadays. So as I said before, the idea that we are just merely typically observers established that the universe can be well modeled through the Feynman method rover support, right? So we always say that our universe seems or appears to be homogeneous and isotropic at large scales or at cosmological scales. In order to test the Copernican principle, what we propose is add new degrees of freedom to this metric to later let the data constrain these degrees of freedom and identify if actually the cosmological data allows from deviation of the Feynman and Meteor-Rover's paradigm or not. And a way to do that many people have been proposed before is use the LTV metric. So as you can see, there is these two metrics are quite similar, but now in the LTV metric, all your cosmological quantities will depend on the radial coordinate. And you also will introduce 3 arbitrary functions. So again, the main idea here is use an inhomogeneous models that are an homogeneous metric that introduce a new degree of freedom, which in this case is a radial inhomogeneity that will be constrained by the data. And then we will identify if this space, the parameter space that the data offers, it is in agreement or not with the Copernican principle. But before to give you more details about the particular model that we use, it is important to say that inhomogeneous cosmology has been proposed also in another context. So, for example, in the beginning of the 90s, or perhaps a little bit before, people proposed to use inhomogeneous cosmology to try to explain the accelerated expansion of the universe. This is just one example. The blue lines represent one inhomogeneous cosmology model, and the data points are data points coming from the supernovae that were available at the time. As you can see, either the inhomogeneous cosmology, which is the blue line, or the lambda CDM model, which is the red line, can't offer a good fit to the lambda CDM or to the supernovae data, right? So because of this, people were again proposed that this model could explain the accelerated expansion of the universe without invoking any dark energy component or without invoking any cosmological. And this is because now your cosmological variables, cosmological quantities, depends on the radial coordinate, and if you have a Hubble, which the partial derivative with respect to the radial coordinate is negative, you will generate an accelerated expansion. And basically, instead of having a faster expansion now than before, you are having a faster expansion here than there. But the problem with this kind of proposals or this kind of models, it was that although we were able, or people were able to explain the supernovae data, the parameter space needed to explain the supernovae data was in large disagreement with other cosmological observations. So here in these enclosed red regions, you will see what is the parameter space that you need to explain the supernovae data. And this green line, green arrow represent which is the typical observational value for the kinetic Sudai-Sedovich effect. The kinetic Sudai-Sedovich effect is a secondary anisotropy that appears in the CMB, which basically in the standard paradigm allow us to constrain the peculiar velocities. However, in the inhomogeneous cosmology, this effect is not longer related only to the perturbation of the universe, but also to the background. So using this kinetic Sudai-Sedovich effect, we can constrain very well how how the Hubble rate depends on the radial coordinate. So again, the constraints even for the supernovae were fine to demonstrate to be in large disagreement with the typical observational value for the kinetics of the isotopic effect. So
Will there be a big dipole also? Will there be a big dipole also if you have ratio?
well, depends. If you are at the center of the inhomogeneity, you don't have any dipole because of the radial symmetry, right? The spherical symmetry.
But they need two coincidences. One
Exactly, yeah. So you are replacing one problem with the other one because you are fine-tuning your position inside of the void or the inhomogeneity. But also depends on the volume of the inhomogeneity. So, but this raises the question so it seems that we have actually confirmed the Copernican principle, right? We have shown that the cosmological data, it is indeed in disagreement with the idea of inhomogeneous cosmology. And the answer is, well, we haven't really confirmed the Copernican principle. What we have shown is that these void models don't work as a viable explanation to the accelerated expansion of the universe. So it means that we cannot replace the cosmological constant of the dark energy component with inhomogeneity, because this will introduce several problems in the cosmological data sets. So saying that, it seems that it is still valid to use it in homogeneous cosmology to study what are the deviations that data allows on top of the Freeman-Lemaitre-Roberts problem. And the particular model that we use to model this violation of the Copernican principle is the so-called lambda LTV model. So as you can see, lambda appears in the name of the model, just to clarify that we are not trying to replace the cosmological constant with the inhomogeneity, but just adding the inhomogeneity as an extra degree of freedom on the model, right? This is the equation that will describe the dynamic of the model, the background evolution. As you can see, the three arbitrary functions appears, right? So M, which is the mass function, is related to the density of matter. This K is just a curvature, and this T is related to the Big Bang time, to the Big Bang time of the universe, right? Or the age of the universe. So because these are arbitrary functions, you have to just make a particular choice for those functions, right? In our case, we try to argue physical arguments to have a particular functional shape for these functions. So we choose to work with the so-called early Freeman-Lemaitre-Roberts cosmology. It means that we are assuming that the universe might be inhomogeneous or might violate the Copernican principle today, but it was highly homogeneous and isotropic at the very early universe. So to do that, first we set the Big Bang time function to be 0, which is basically assume that the age of the universe doesn't depend on any radial component, and the Big Bang starts at the same point, or at the same time in all the points of the universe, right? We also assume this particular form for the mass function, which just came from an extra gauge of freedom that the model had, and we assume a compensated curvature profile. This curvature profile is called compensate because exists a finite radius in which you match the lambda CDM model. So you can recover the lambda CDM background at a particular radius, and this radius it is denoted with RB, this quantity here. So you can understand this model as a lambda CDM model, which is endowed, a lambda CDM background, which is endowed with spherical inhomogeneity. That could be an overdensity or an underdensity, right? This is just a plot showing how the matter density contrast, which is the blue lines, evolve, and how the mass density contrast, which is an integrated function of the matter density contrast, evolve with the radius, right? So all the fluctuations are set to be 0 in this radio because we are just recovering the lambda CDM background. And this is a very useful trick as well, because at some point, if you want to include cosmological data that is related to perturbations, that could be, especially at the early universe, that could be lambda CDM, you need to build up effective framework in which you can transform the prediction of the lambda LTV model in just purely lambda CDM predictions. Okay.
So the size of the overdensity is whether 1 or 10%, is that right?
This one is 80%. You mean the amplitude or?
Yeah.
80% is in this case, because it's 0.8. This delta zero describes, the over the under density in this case at the center.
At redshift 0 or at the big value?
No, this is this will be the size. So this redshift describes the size of the inhomogeneity in the redshift coordinate. But if you can see it's more or less 2 gigaparsec. You go to the radial coordinate, and the under density is around 80% less than the background. And this whole picture is today.
But what would it be at the, I'm just trying to understand if it's commensurate with what we expect, whether it can be -5 or so. What's the typical size of density presentations?
Yeah, this is something that I will discuss later, in which we propose something that can relate this the parameter space of this model with the typical perturbations that you expect from the lambda CDM model or from the Friedman method of superposition. And this is actually basically started this slide. So again, the model that we are using is basically a lambda CDM. A lambda CDM background, which is endowed with a spherical inhomogeneity. And this is just some simulations produced by Professor Valerio Mara for the BHOMO project. This panel on the left is the lambda CDM simulation, and the other two panels are a lambda TV model with a density constant which is positive and a density constant which is negative. As you can see, the main difference is just that you have now a spherical inhomogeneity at a particular scale, right? And then beyond of the radius RB, you just recover the predictions or the lambda CDM backgrounds. So this means that you can describe this model, this lambda TV model, just using 8 parameters, the typical 6 parameters coming from the lambda CDM plus 2 parameters, which is the delta naught, which is the contrast density at the center of the inhomogeneity of RB. You will see that through this talk, you will see another variables like delta L or the capital delta 0 or RL. More or less, they are interchangeable. I mean, the physical picture it is the same. Okay, but related to the question of Guilherme, so we are saying, or the cosmology of the Copernican principle established that we occupy special position in the universe, and because of that, we can model the universe with the Friedman method over Walker plus perturbation. And this plus perturbation is important, right? Because this means that will be a portion of the parameter space of the lambda TV model that will correspond to simply Friedman method over Walker. So it is important to have something that benchmark which is the parameter space that is expected to be understandable or consistent with the Friedman limiter also Walker metric, the perturbation of it, and actually the Copernican principle. So in order to do so, we propose the Copernican primal. Let me skip this slide because it's more or less the same, right? The picture or the question how we can distinguish if this is something that violates the Copernican principle or is something that is actually in agreement with the Friedman derivative rules for perturbations. So in order to create this benchmark, distinguish which parameter, the portion of the parameter space that can be understood as the Friedman derivative rules for perturbations, we propose this Copernican prior. So basically, we take the power spectrum coming from the standard paradigm from the lambda CDM model and construct this prior, taking into account the variance generated by this power spectrum and see how much deviation or fluctuation we can have around the Friedman limiter over Walker. Of course, this prior doesn't work by itself. You need also to include any proof, and the proof that can tell you about the Friedman limiter over perturbations is the likelihood of the lambda CDM, right? So basically, we are saying which are the fluctuations that the CMB model, the CMB observations allow to have in the Friedman limiter over Walker metric, and how we can translate these perturbations in the parameter space of the lambda LTV model. Saying that, we have our first results, and you can ask questions because I'm seeing that they have plenty of time now. So I was a little too fast at the beginning, I guess. But anyway, so these are the constraints that we obtained using current cosmological data.
Also, let me ask you a question. Can I understand this as a modification of the power spectrum? It means that there's a certain scale at which it's likely to generate a perturbation that is higher than the typical amplitude of these two parameters. Couldn't you have said that, oh, instead of AS and NS, I have a 4-parameter model of the power spectrum density perturbations and
Yeah, but the problem is, I mean, how would you interpret this AS and NS? I mean, because yeah, so somehow you are inflating, let's say, the perturbation that you can have in the universe, right? And this will modify the power spectrum. But I'm not completely sure how you could put that in the picture of the Copernican principles, right? And actually, the way that the perturbation in homogeneous cosmology evolve or behave is not well understood yet. And this is something in which Professor Valerio Mara is working right now with the simulation. So it will be difficult to translate how this kind of fluctuation generated by this homogeneous model translating into the typical power spectrum of the lambda CDM model. So I guess there is not that the 2-1 correspondence.
I would have said that there is a typical scale at which the power spectrum has a peak or so, and it just so happens that we live in a bubble where we're sampling with 1 mole coming from this. I mean, that's what people are doing, for example, not to generate primordial black holes, right? Take different motivation. We take the power spectrum instead of being flat. We put like a big peak at short scales. And you have the big perturbations, certain size.
Yeah, I don't know then. I mean, not completely sure how. I guess I understand that the general picture, but not completely sure how you could relate that with the Copernican principle. Because here the idea is just allow this radial homogeneities over the metric, and then see what data tells you about that.
I mean, in the case of primordial, because people put a peak localized in K space. Here you want to put a peak localized in dire space.
That's right. You would change. It would be broad then.
K space.
That inside, I didn't quite understand. Sure. Last one year prior. So can you explain again the 3 expressions on this slide?
Sure. So sorry. So this is the so-called Copernican prior. So basically, you are saying, given the variance that is produced by the power spectrum of the lambda CDM models, how much fluctuation you can have, right? How much or how big is this delta? The problem, but by itself, the Copernican prior doesn't constrain anything, right? Because it's something theoretical, and you need to add some observation to do that. And the observation that we choose is the CMB data, right? Which is already tell us about the fluctuation of the temperature of the photons that were released on the large scattering surface. So basically, we are just saying all the perturbations allowed by the CMB should be converted in perturbations or thermal emitted Robertson perturbations that should be converted in the lambda LTV parameter space. Okay, so this green contour represents the constraints coming from the Copernican prior together with the CMB, and are the ones that we are understanding as the lambda CDM perturbation, right? So anything that goes beyond this green area will represent a violation to the Copernican principle. And the constraints given by the data are this red region and the black contour as well. I will just ignore the red region right now. I will talk about that later. It's quite interesting, but not just focus on the black contour, right? So if we compare the black contour with the green contour, we will see that this portion of the parameter space is still allowed by the deviations of the Copernican principle, right? But in general, we can say that cosmological data can tightly constrain the parameter space of the lambda TV model, which will tell us about the Copernican principle. The typical fluctuations or the typical no-Copernican fluctuations allow in this region of the parameter space that very small, has a value of around 0.01. And if you compare the area which is allowed by the data and the area which is allowed by the Copernican prior, we see that in general, in all different parameter space, it is the ratio between those areas around 1. But of course, this is misleading because we can see that the portion that is driving difference is even at scales greater than 200 megaparsecs, right? If you only compare this portion, you will see that the ratio between those areas goes more or less between 3 and between 2. So we need to improve our constraint by a factor of 2 to fully convert the Copernican principle, especially in this portion of the parameter space. Something that we also found is that that dropping the assumption of the Copernican principle does not worsen the constraints on the typical cosmological parameters. So basically, either if you use lambda CDM or lambda TV model, we will obtain the same constraints in the typical parameters related to the lambda CDM background. So this is somehow pointing to the fact that we are now at least reaching the point in which we can drop the Copernican principle and have the same accuracy that we will expect in the standard picture. Of course, within this framework, within this particular framework, which is the most simple or the simplest case that you can assume to test the Copernican principle. These are the results regarding the forecast analysis that we perform. We use or we try to understand what will be the improvements in the constraints if you add LSST data, BAO measurements coming from DESI, and also measurements coming from Euclid. And we found that in general, the combination of these next generation surveys will improve our constraints up to a factor of 40%, especially in that parameters and the region of the parameter space that we still having fluctuations over the Copernican principle, right? This means the regional parameter space that considers scales that are greater or around 200 megaparsecs.
Are you using the whole matter power spectrum or just the BAO peak?
No, it's just the BAO distance.
Did you try the whole matter power spectrum?
No, because again, so we don't have any template for the matter power spectrum in the homogeneous cosmology. But it will be quite interesting. I guess it will be a more powerful proof, right? But it's something that we still need to understand how the power spectrum will behave, or how you can compare that power spectrum with the lambda CDM power spectrum. We also found that the future data will be capable of detecting no-Copernican structures. And in this case, we generate more catalogs assuming the values given by the black star, which correspond to an amplitude of 0.1 in the matter fluctuation, with a size of around 0.75 in the redshift. So this detection will occur, we live in a not Copernican structure with a significance or greater than 3 sigma. So regarding the Hubble tensions, I haven't mentioned what is the Hubble tension, but just let me tell you, you are already, I guess you are already aware of what it is, but anyway, it is the disagreement between the late time and early time determination of the Hubble constant. So there is a systematic disagreement that you can see here on the left. You have the measurements for the constraints that are obtained mostly using CMB and other proofs related to the early universe. On the right-hand side, you have the constraints using model-independent techniques, mostly that relate to the late universe, or to the late times of the universe, right? And you can see that there is a big discrepancy between these two kind of determination. This discrepancy can be or can reach the 5 sigma level if you compare the constraint coming from Planck with the constraint coming from the Schuster collaborations. So because of this, many people have been has proposed to explore new physics or the existence of new physics capable of explaining this discrepancy. And of course, one natural way to do that is assume that you have a value of the Hubble constant, the CMB, and a different value at local scales. And the model that can do that in theory is homogeneous cosmology, right?
What about these TRGB measurements? They are consistent CMB. What's the status?
Yeah, the TRGB measurements are quite interesting, to be honest, because they seem to be consistent with both. There is a kind of debate now in the literature and in the scientific community of, I mean, why this difference is dry if you compare with, for example, constraint coming from surface. So I'm not an expert on that, sorry, but yeah, I will just pass over that. That's been what does TRGB? TRGB is
Tip of the red giant.
Yes, another way of calibrating supernovae, because to measure the Hubble constant, you also need complementary astrophysical distance that tells you what is the absolute magnitude of the supernovae. So depending on which calibrator you use, the value of the Hubble constant will vary. So if you use this TRGB, you have a value of the Hubble constant which is lower compared with the one you obtain using surface or other astrophysical distance to calibrate the supernovae. So we explored this possibility, and actually what we found that in general, the inhomogeneous models cannot solve the Hubble tension, but there is a funny, let's say, a funny thing going on in these blue regions. So these constraints in blue are obtained when you consider the combination of CMB data and the supernovae that are used to constrain the Hubble constant using the cosmic distance ladder. So it seems that there is a kind of fluctuation over that supernovae that allows you to have or to live in a non-Copernican structure that disagree very strongly with the Copernican principle. However, once you consider the whole data set of supernovae, which is these red regions, you see that in general the cosmological data constrains the model to be more or less consistent with the Copernican peak, from the Copernican picture of the universe, and because of that, the value of the Hubble constant that you infer is just consistent, only consistent with CMB, but in tension with the local determination, which is in this kind of pink region. See here again, if you only consider the local supernovae that are used to measure the Hubble constant, which is given by these results in blue, you will see that model generate a value of the Hubble constant which is consistent with local determination. But if you consider all the data set of supernovae, this preference for a higher value of Hubble constant disappears. It means that in general,
what C do you use? What redshift determines low versus all?
Yeah, so the whole data set, this is actually for the previous release of Pantheon. The whole data set go from 0.01 up to 2.3 more or less, and the low C goes from 0.023 to 0.15, which is basically the same supernovae, or more or less the same supernovae that you use in the cosmic distance ladder technique to measure the Hubble.
And have you explored outside of the inhomogeneous model, just a standard FLW, the same kind of splitting?
Kind of, like I can show an initial slide here, but just let me continue because I don't have any time. Let me go just to the conclusions. So, okay, we have found that cosmological data can constrain very well the Copernican principle, although we still have non-Copernican fluctuations at the scales that are greater than 100 megaparsec, actually 200 parsec. If we draw the assumption of the Copernican principle, we don't grow the constraints on the typical cosmological parameters. This is quite important. We actually have shown that future data will improve our constraint up to a factor of 40% on the constraint of the Copernican principle. And actually that we will be able to detect non-Copernican inhomogeneity with a statistical significance that is greater than 3 sigma. Also, we have found that inhomogeneous models cannot solve the Hubble tensions. It only does if you only consider a particular data set of supernovae. And this is something that I skip, but the best fit of the current cosmological data seems to be consistent with a shallow void of this amplitude and with this size of 300 megaparsec, which interesting, it is in agreement with the Copernican principle at the 2 sigma level. So that's kind of funny question there as well. But more important, let me just point out that our results correspond to nothing more than the first steps to the development of inhomogeneous precision cosmology, because the assumptions that we have used through this work are very particular, are very constrained. That will be all the thing.
So any further questions? Do you have a model of what could give rise to this void in the beginning of the universe?
No, it's just a phenomenological model. I don't think we have a theoretical model for that.
Loop correction to the input on potential.
And another question: how far can we be from the center of the void?
Yeah, and in this particular case, we assume that we are the center of the void. So it's a
1 megaparsec only can already detect.
So if you want 1 megaparsec away, I guess you have a dipole that it would be inconsistent with the CMB.
What is the limit
If you move from the center of
much?
the motionality, 1 megaparsec.
Already 1 megaparsec is already.
If I remember correctly, or maybe not, but
Sorry, I thought we always subtract the dipole, so whatever it is, we subtract the dipole. It's per cube, maybe it's because we're not the center of the void. What would you see when wrong?
what do you mean by
Maybe it's a higher anisotropy. The dipole is always subtracted from the CMB.
yeah, but it is a constraint anyway. Like, because in this case you will have, I mean, you will have to argue that part of the dipole of the CMB is produced by the fact that you are living in an isotropic universe, and it's not isotropic anymore. Because so far the assumption is that the dipole is generated, but because of the peculiar velocity that we have with respect to the local group, right? So you will have to argue that on top of that you have another contribution coming from the fact that you are away from the center. So this is the main constraint that you have to put the observer at the center. Of course, you can do better. You can move around the center. This is something that we didn't investigate that much because it's already quite complicated, to be honest, in the numerical part when you try to solve the cosmology and so on. But this is something that we plan to explore in the future.
I mean, there are these claims by Sarkar that the dipoles from galaxy clustering
is in tension with the dipole that you made from the CMB. Yeah, we also somehow have a going on project in which we try to use this model with the observer away from the center to see if we can somehow explain the dipole. If I remember well, the preliminary results were that it was a little bit difficult because mainly also the kinetics of the isotopic effect constrain very well this kind of peculiar velocity that you will have you move away from the center.
Okay, let's thank David again. Now we're going to have the last talk of the day. It's going to be online by Luis.
Hello,
Hello, Luis.
can you hear me? Hello.
Yes, so far the volume is low, so hold on just a second. Oh, it's Luis with the right X, not with the Z. Okay.
So am I able to share my screen now? It
Yeah.
seems that I am.
But can we increase the volume?
Because the internet.
The internet, the volume? How will the internet affect the volume?
Is it on my end or in your end?
No, okay, we can see the slides. Maybe the volume, can we?
Can you pump the volume?
Try to speak now, Luis.
Not good.
Hello.
Yeah, we're good. The only one thing is
Is it on my end or in your end? But
we're good. We're good. So you can go into
okay,
go into slideshow.
presentation mode
Thank you. Go ahead.
is okay. So first of all, thank you for the invite for presenting here, and thank you for awarding me a honorable mention in the prize for this year. And as Professor Luis said, I did my PhD in University of ABC, but right now I'm a postdoc here in Germany in Jena University. And today I'm going to be talking about my PhD thesis, where my advisor was Cecilia Chiranti, my co-advisor Mauricio Richards in UFABC Brazil, but I also did works in collaboration with Professors David Redis in PSU and Professor Nayash F. Shorty in Perimeter Institute. So my thesis was entitled Prospective Sources for Gravitational Waves for Third Generation Ground-Based Observatories. And I would like to break this title in parts. And first, just a small overview of what are these third generations detectors. And we all here should be familiar by now with the current network of gravitational wave detectors, which is constituted by LIGO in the US, Virgo in Italy, and Cargo in Japan. And they are the so-called second generation because they have they have technological upgrades on top of the first design of LIGO. But even though they have been detecting gravitational wave sources almost on a daily basis when they are turned on now, we know that they are not almighty in the sense that some sources can be lost either because they are too faint or too far away to be detected. So there are projects to upgrade, to build new detectors with new technologies. And the main two efforts that I'm aware of is Cosmic Explorer and Einstein Telescope, which constitute the so-called third generation gravitational wave detectors. And what I'm showing here, just for means of comparison, is the sensitivity of the first generation LIGO in light green and the second generation network showing an improvement of at least one order of magnitude, even more, compared to this first generation detector. And moving to the third generation, we have another order of magnitude improvement. And with that, it is natural to ask what kind of science cases we are enabling when constructing these detectors. And that is where my thesis was focused. And I mainly studied two science cases. And the first one that I want to talk about is what we call accretion-induced collapse of white dwarfs. Again, a long title,
Luis?
and I want to break it by parts. First, hello?
Yes, can you kill your video so to see if that improves the internet? Thank you.
Okay. Is it in presentation mode now?
Yes, go ahead.
Okay. So just a small overview of what are white dwarfs. They are the final stage of low mass main sequence stars. They do not burn their fuel up to iron, so they are still composed to elements lower than iron in the periodic table. And two main compositions of these stars are carbon oxygen or oxygen near magnesium. And because they don't have the nuclear thermonuclear reaction in their core, they're actually supported by the electron degeneracy pressure inside of this star. And what it so happens that this electron degeneracy pressure can only support total mass that is proportional to the square of the electron fraction. the electron fraction being the ratio between the electron density and the nucleus density. And this value of total mass implies that if this star accretes more material, surpassing this maximum value, this star will become unstable and will collapse and will trigger an explosion event, which is kind of counterintuitive because I'm calling a collapse, but I will explain in the next few slides what will trigger this explosion. So in the code that in the context of this project, we worked in numerical activity, and we used the WSGT code that is based on the Einstein toolkit. And here's a little bit of the setup that we use, but I won't get into much details about this. But the idea is that the improvements that we have compared to previous works is that we did full GR and 3G, where in previous works, the simulations were either 2D or in Newtonian gravity. So we evolved 3 different models, basically differing by the rotation profile of the star. We did one model that is non-rotating for means of comparison, and 2 highly rotating models because we expect these stars to be highly rotating due to the accretion history that is triggering this collapse. So what is happening is that this star is supported by the electron degeneracy pressure that is due to the Pauli exclusion principle of electrons in the core of this star. And when it accretes more mass to suppress the maximum value, it becomes more favorable to the protons to capture the extra electrons and form a neutron and emit a neutrino. In this process, the electron density will go down, and as the pressure of the electron degeneracy is proportional to a positive power of the density, this pressure that supports the gravitational collapse will shut down and the star will begin to collapse. And this is what is happening inside this star. At first, here I'm showing the velocity profile of the center of this white dwarf. At first, you can see that the velocity profile is basically inwards, and this configures the collapse, but at some point you have an outgoing motion, and at least for the rotating models, you have these nice spiral arms that expand throughout the evolution. And what is happening here is that the core of the star becomes very dense, as you can see from the density profile as a function of time here in the left. But when it reaches densities that are very close to the nuclear saturation density, it can't be compressed any longer, and it suddenly expands, and therefore you have this relaxation seen here by this decrease in the density, and this sudden relaxation is what injects a lot of kinetic energy in the fluid, and therefore you have this explosion that we are seeing here. But the rotating model, it's a failed explosion. You can see that the shock has stalled and the explosion is not expanding over the whole evolution. So we see that we have mass motion. This is one key element for gravitational waves. But another key element is mass asymmetry. And for that, we study the mass distribution of these stars. And we perform a mode distribution as shown by this integral here, and decompose the density profiling modes. And what we see is that for the non-rotating case, the mode excitation is very low. We could see that by the previous plot because they are basically spherically symmetric. But in the case of with rotation, we can see that in between 20 and 80 milliseconds after the core bounce, that is the expansion of the core, we have a domination of the n equals 2 mode. And this is where the quadrupole contribution is very strong. And this we can see in the bottom left image where we see the density fluctuations, a nice quadrupole configuration where we have 2 underdense regions opposed to 2 overdense regions. And at late times after 80 milliseconds, we have m equal 1 mode lingering on that is related to the 1-arm instability. And we can see here in the bottom right as a nice dipole moment where you have 1 overdense region opposed to 1 underdense region. And of course, for the rotating models, you have in a nice thick disk around the equatorial plane, as you can see here in the top images in both plots in the left and right. So if we have mass motion and mass asymmetry, we have emission of gravitational waves, and we evolved this the gravitational wave of this signal of this event both by a quadrupole mode approximation and via Psi4 reconstruction of the waveform. And we found that these events have a very large contribution in the kilohertz band, where is a region that will be nicely explored by third generation detectors. And we, in order to make a estimation of the SNR, we place these models at 10 kiloparsecs from us, meaning within our galaxy. And for means of comparison, LIGO would see these events with an SNR of 10 to the 3/9 and 910 to the to 1,000 as SNR, whereas the Cosmic Explorer and ICTP telescope would have at least a factor of 10 improvement compared to this to LIGO, which would imply event horizon that would change from 1 megaparsecs to 8 megaparsecs in the case of a Cosmic Explorer. And this is very nice because in 1 megaparsecs, we basically have only the Milky Way and Andromeda in this region, but in 8 megaparsecs, if I'm not mistaken, by a catalog that I have seen, we have at least 400 galaxies in this space. So this would increase a lot the chances of detection of these events with this new network. Not the focus for this talk, but I also looked into the multi-messenger emission of this event. We look into electromagnetic radiation and neutrino emission. And what we see is that in electromagnetic band, these events are mainly 2 orders of magnitude fainter than a supernova type 1a, which at first could seems bad, but it so happens that supernova 1a are very, very bright. So these events are still very likely to be seen by optical telescopes. And in the neutrino emission, they are very similar to core collapse supernova, meaning that they would have similar detection properties to these events. The second type of events that I study in my thesis is more speculative in nature, in the sense that we want to propose tests of general relativity, and we want to answer the question whether black holes actually have an event horizon or not. So the idea here is to study what we call in the literature as exotic compact objects or black hole mimickers, depending on the authors. And the idea is that this ECOs, they are very compact objects, but instead, almost as compact as black holes, but instead of having an event horizon, they have a surface that is barely above, just a little bit above the would-be horizon. And the position of this wall is given by this R0 naught here, which is the tortoise coordinate of the surface. And it's just infinitesimally larger than the position of the event horizon. This effective model is inspired by a lot of proposals that came in the literature to try to solve the information paradox, where you have space-times that could mimic black holes, but they don't have an event horizon. And I cite some models here, but in my work, we did a more model agnostic approach to construct these objects. And it's important to say that these objects need to be very compact, almost as compact as black holes, because what will happen here is that this surface will create acoustic cavity in the potential, the gravitational potential of the space-time, as you can see in this plot. And this acoustic cavity will trap the gravitational waves. And what will happen is that the gravitational wave will bounce back and forth inside this potential. And periodically, a little bit of gravitational wave will leak and will reach spatial infinity again. If this cavity is not large enough, meaning that the object is not compact enough, the first echo, gravitational wave echo, the first pulse that will arise, would be able to overlap to the quasi-normal mode ring down of the black hole potential. This would make a deviation that would already be seen by LIGO, and therefore we have to assume that this object is very compact in order to agree with current observations. So contrary to the previous part of this talk, we worked in the perturbation theory framework, and to do that, we solved the Tucholsky equation in the with the Green's function technique in this frequency domain, and we did this by changing the boundary conditions at the would-be event horizon. And carrying out the math, what we see is that the Green function is described by a term that is exactly the black hole's Green function, plus a second term that is proportional to what we call the transfer function. This transfer function will be a function of the asymptotic amplitudes of the homogeneous solutions to the Tucholsky equation, and of this curly R, that is our model dependent reflectivity, that is dependent on your underlying quantum gravity, let's say, and this phase factor that just take into account the time travel inside the acoustic cavity. In our particular case of study, we use this reflectivity model that is given by this paper by Oshita et al. In 2020, where they propose a Boltzmann-like reflectivity, which is proportional to this exponential factor, where kappa is the frequency in the event horizon frame, and pH is the temperature, Hawking temperature of the black hole. And this alpha parameter is just a phenomenological parameter that we vary just in order to be able to impose constraints to this reflectivity. So what we are most interested in this study was the impact of the mass ratio of a binary in the black hole's echoes. So what we did, we studied, we evolved 5 different models with different mass ratios, and just for consistent check, we did evolve the gravitational wave from the black hole part of the Green's function, and we see that we have the nice spiral merger ring down form as expected. But then we move to the first echo, as it would be the louder echo, and we chose to analyze the time of peak of the first echo and the amplitude of this echo, as this would be the two main properties to estimate in the parameter estimation of our underlying quantum theory. This is, we saw that the time of peak of this echo and the amplitude change with the orbital, the mass ratio of this this binary system. And what happens is that we have louder echoes for comparable mass systems, and the time of experience of the first echo also is earlier for this comparable mass binaries. And what we argue is that the time of peak of this first echo is very important when determining the position of the reflective wall, and this the change of in the time of peak of the first echo, as it's proportional to the size of the acoustic cavity. This would lead to a error in the estimate of the position of the wall of 130%. So even if you have a model selection, you have to take into account the orbital effects of this binary in order to separate the true quantum theory that is dictating these exotic compact objects. We did also study the effect of rotation of the final object in the echoes, and what we see is that if the final exotic compact object is highly spinning, the echoes would be stronger. They would have a slower decay rate. They are more well separated, and they have this double peak structure for later echoes. And these are easily understood because the time separation between the echoes is proportional to the size of the acoustic cavity. And just as in the case of a black hole, a Kerr black hole, the object is more compact with more rotation, so you have a larger time of travel inside this cavity. The echo being stronger, it's mainly due to a larger effect of superradiance, and therefore this would lead to a stronger signal. The double peak structure is just because you have two families of modes traveling inside the acoustic cavity, one that is co-rotating with the black hole and one that is counter-rotating, and this leads to slightly different time of travel inside the cavity, and therefore you have this double peak structure that gets stronger and stronger for later echoes. We studied the detectability of these events within LIGO structure, and what we see is that varying the alpha parameter that I mentioned before, the best case scenario, as we said, is for a comparable mass event binary, and if we have an event that has a mass ratio similar to GW150914, we would have to find an event with an SNR of 60 or 20, depending on the alpha parameter, to have a SNR of the first echo 8. And just for means of comparison, GW150914 had an SNR of the full event of 20 something. So we did an estimate that for LIGO in the fourth observation run, this would mean that depending on the choice of a parameter, this would be 10 to the minus 2 or 10 to the 0 events per year with the detectable echoes. And the fact is that the 3G detectors will have improvement of 10 to 100 in sensitivity. So these event rates with detectable echoes will also improve for similar factors. And therefore, we can use these detectors to put way more stringent constraints to this modified theories of gravity. With that, I will end my conclusion saying that accretion-induced collapse of white dwarfs lead to gravitational waves that are detectable up to 8 megaparsecs with Cosmic Explorer. The detection rates that we expect there is 1 every 15 years, given that we have these 400 galaxies inside this event, this detection horizon, and that in the neutrino and electromagnetic emission bands, we also have good prospects of detections. And for the case of gravitational wave echoes, we have seen that 3G detectors are the way to put very nice constraints to these theories, and it will enable us to impose tests of the existence of event horizons in real in your real data. So with that, I thank you for your time, and gladly will take questions.
Thank you, Luis.
You can see our crowd now.
Yeah, so maybe you should also turn your camera on. So any questions? Aaron?
Hi, Luis. Thanks for the talk. I was curious about the accretion-induced collapse study. So I understood that these were potential channels for type 1a supernova, but it sounded like your simulations didn't include nuclear burning or possibility of detonation. Can you comment on whether or not you expect type 1a explosions in these kinds of accretion-induced collapse?
So can you repeat? I think that I lost some words. I think that you asked me to comment why there is no thermonuclear burning in these events. Was that the question?
Essentially, yeah. If they're if you expect these to detonate in type 1a supernova.
Okay, so this was a work assumption that we did. The actual during the triggering of the collapse, you could have a detonation of a thermonuclear explosion there, and this is what drives a type 1a supernova. You're correct. But during the collapse of these events, we assumed by hand nuclear statistical equilibrium and just a simple de Leptonization scheme where you only have the electron capture process. So in a way, our simulations will never trigger a supernova type 1a, because we were specifically interested in core collapse supernova by the electron capture process.
Okay, thank you.
Any other question? So I have a question, Luis. Is there an estimate for the expected rate of accretion-induced collapse per galaxy? I mean, I don't know about this.
This is highly uncertain. We did I estimate that is we put a value that is 1 every 15 years in this event horizon, and in this detection horizon. And to do that, we said that the event rate would be 10% of type 1a supernova, meaning per galaxy. And then we multiplied by the number of galaxies in this event horizon. That's how we got this 1 out of every 15 years in Cosmic Explorer. But one would have to place some, I think that the real constraint in this event rate will be imposed by nuclear synthesis. So we have to check how many have elements it generates, and what is the proportion of these elements in the universe that are produced by accretion-induced collapse. So this is the last part where I don't think that we have much understanding. So the values that I always see in the literature assume that all have elements are constructed are made up by accretion-induced collapse, and they have similar numbers to mine, but this would be considered optimistic value, I would say, as you have other nucleosynthesis sites other than accretion-induced collapse.
All right, thank you. Any other question? So if not, let us thank Luis and David. Thank everyone.
Good night.
Right.
In the mix for